Nature. It's a source of life, it's energizing, it's ephemeral, it constantly surrounds and inspires us. Architecture has largely replaced the natural environment with static and high energy consuming buildings. There seems to be a lack of curiosity in exploring how forces of nature can animate our spaces. How can we design kinetic architecture that imitates the perpetual metamorphosis of nature? More specifically, how can we design a spatial automaton that reacts to natural energy inputs, such as the speed of the wind, or the weight of the rain, or the heat of the sun? To answer that, let's first check out the evolution of tools, engineered systems, and kinetic architecture.
Sometime in the Stone Age, early nomads invented the tent, freeing themselves from stationary residence. A couple thousand years later, the wheel and axle were invented, allowing for further and faster mobility. The same circular motion would later be used in the pulley, which allowed for easy vertical mobility. The invention of the screw then converted the circular motion into linear motion. These simple machines could be combined and arranged into more complex systems for different purposes. Armies used them to create weapons like the trebuchet. Ctesibius of Alexandria used them to develop the field of hydraulics, inventing mechanisms such as the cuckoo clock, which used a steady flow of water to measure time. Inspired by this work, Archimedes of Syracuse used his mathematics background to understand and record the principles of simple machines, inventing systems himself, such as the compound pulley. Heron of Alexandria picked up the baton next, experimenting with non-human powered systems, such as the wind-powered organ and steam engines. All this knowledge contributed to the construction of great structures. In some cases, the system would be part of the architecture, such as the pulley-operated roof of the Colosseum. In other parts of the world, the construction of systems were embedded in tradition, like the annual Inca grass bridge ceremony. In China, innovations were made on the water clock, particularly Susong's astronomical clock tower, which not only kept a relatively accurate time, but also featured rotating globes and figures ringing bells in its systems. Skipping through the Dark Ages, we end up in the Renaissance, a period about the rediscovery of ancient texts. Leonardo da Vinci was greatly influenced by these texts, particularly fascinated by Archimedes and Heron's work. He endlessly invented and innovated systems including the Codex Atlanticus clock and the aerial screw. It was during this period that disciplinary crossovers led to kinetic architecture systems such as Solomon Ducos' pleasure gardens. This French hydraulic engineer was greatly inspired by Heron of Alexandria's work. Later on, the invention of the battery changed the way things were powered. Mechanical systems would no longer need to rely on water, wind, or human strength to operate. One such example of an early kinetic architecture was the Villa Girasol, which followed the movement of the sun using a track and electrical motor. The computer was the next radical change for kinetic architecture. Along with electrical energy, it allowed for the complex string of action to be reduced to the push of a button, or in some cases, simply automatic. One such centrally controlled system is the Rogers Center, which features an operable roof. The Al-Bahar towers feature a kinetic facade that open and close to regulate temperature and lighting. Same is the case for the One Ocean Pavilion that has fins that open and close. The MIT Media Lab has taken a different approach to kinetic architecture by developing materials that are self-actuating to be used as building blocks for response systems. This project wishes to continue the lost exploration of a computerless relationship between kinetic architecture and nature, proving that a network of simple mechanisms can be triggered by natural energy inputs to create a perpetual spatial performance. It's a simple formula. From observing forces of nature such as sun, wind, rain, and snow, and then extracting a physical property from them such as speed, light, humidity, weight, or temperature, we can then use these physical properties as actuators that trigger a chain of simple machines combined of pulleys, screws, levers, and ramps to create a spatial output. I searched and recorded precedents of such a formula being used, fastidiously trying to understand how different engineering systems worked. I greatly admired the creative dialogues created between different inputs and outputs. These precedents were categorized into system types ranging from pneumatic to smart materials, and then the kinetic properties they exhibited ranging from transformative to expanding. This helped me design new relationships between architecture and engineering. Starting off with the rain-responsive pavilion, which used polar linkages and counterweights that were triggered by the collection of rainwater to create a spatial transformation. I built this system to experiment with how it would work. I also turned it into an animation that more clearly told the story of its function. Next was the wind-responsive pavilion, which used pulleys, a screw pipe, and sails triggered by both human input and wind to create a spatial flexibility. I also built this system as an experiment of its function. A supplemental animation revealed how the screw pipe could be turned to deploy seating, and how the sails and pulleys worked together to provide shelter from the wind. Next was the sun-responsive pavilion, which was a combination of gears, sundials, and a zoetrope that used the light of the sun and human input to create a new way of telling time. Unfortunately, the model didn't work due to incorrect gear tolerance, so instead I made a video that speculated its performance. 2 gear chains, one clockwise and the other counterclockwise, were attached to a bicycle system that spun a zoetrope. At the right speed and at different times of the day, one of 3 animations would be cast on the ground. Next was the fire-responsive pavilion, which combined the shape memory alloy with origami triggered by the heat of sun or the fire to transform. I experimented with the shape memory alloy known as nitinol for this model. In the animation, it can be seen that when a fire is started in the center, the origami fire pit rises like a tower of fire towards the sky. I decided to revisit the rain-responsive pavilion to improve upon the design and functionality. This time, I theorized the use of siphons and bar hinges to create several spatial variations. I started with exploring different chipboard bar hinges and then transitioning to wooden ones. These led to the Rain-Responsive Pavilion 2.0. As can be observed, when it rained, a water collection system would weigh down a network of bar hinges that then stretched out to deploy a shelter from the rain. My journey led to a more refined and final version of the Rain-Responsive Pavilion.